for year 13 physics, simple harmonic motion. This lesson has to do with energy and simple harmonic motion, as well as about resonance. So let's get right on with it. So the speed of an object moving in simple harmonic motion is not constant, it is changing. And so the kinetic energy of an object in simple harmonic motion is changing. So if you look at the pendulum, when it's swinging the fastest at the equilibrium position, that's where the kinetic energy is the maximum. At the end positions, when it stops before turning back, all the energy is potential, and midway, it's a combination of both of them. Similarly, for the spring, the energy is all kinetic at the equilibrium position where it's moving fastest. Kinetic energy is zero at the end positions. However, the elastic potential energy is a maximum at the end positions. Now, if in an ideal condition, there's no energy lost in the form of heat because of the force of friction, then the amplitude remains the same. The amplitude is an indication of energy. So the total energy remains the same. So this graph here shows my blue is the gravitational or potential energy, could be elastic or gravitational, and that is your kinetic energy. They kind of, that's the way they go. Okay, so when kinetic energy is a maximum, your potential energy is zero. And this one is at any instant of time, the total energy always stays the same. So kinetic energy is the maximum at the equilibrium and zero at the end position, and the equation for kinetic energy is half mv squared. The potential energy depends whether it's a pendulum, so it's your EP equals mgh, or for a spring, it's half ka squared, where a is the amplitude. Now, in reality, what actually happens is some energy is lost to the surroundings in the form of heat due to friction. So if energy is lost, then there's going to be a decrease in amplitude. However, the period remains the same. So this is called damping, and these oscillations are called damped oscillations. So the way we draw damped oscillations is you need to mark off exact values for the period, because the period doesn't change, and depending on where the oscillation starts, so I've drawn this for starting at equilibrium. If something has been pulled down and released, you need to start it from there and draw your graph. You first draw the decay curve, mark your period, and then you draw your damped oscillations. And this is one oscillation over here, 2, 3, 4, and I've got 5 oscillations. Now, where do we use this? It's used in shock absorbers in car. The beehive also has shock absorbers under the building to absorb the energy from earthquakes. Now, moving on to forced and free oscillations. Any object that is free to oscillate, like a spring or a pendulum, if displaced and left to oscillate, will do so with its own natural frequency. These oscillations are called free oscillations. In reality, the amplitude of these oscillations decrease with time because of damping. Okay, sorry, that's my dog. Forced oscillations. Alfie, quiet boy. If an external force called the driving force is applied, the object will vibrate with the frequency of the driver. If the frequency of the driver is quite different to the natural frequency of the object will vibrate with small amplitudes. So what is resonance? When the frequency of the driver matches the natural frequency of the object, then the object will vibrate with very large amplitudes, as there will hardly be any energy losses. This is called resonance. The frequency at which this happens is called the resonant frequency. So over here, this is displacement against frequency. So for some frequencies, the amplitude is very small, and then it suddenly becomes very large at a particular frequency, and that is my resonant frequency.